Starting with this example, we're going to be looking at the second law for different types of processes. In this problem, we're going to be studying second law for an open system process. Alright, the problem says we have steam at 7 megapascal and 450 degrees Celsius is throttled in a valve to a pressure of 3 megapascal during a steady flow process. And it wants us to determine the entropy generated. There's actually a typo. This should be the entropy generated per unit mass during this process. So that's what the problem says. What we're going to do, we're going to set this problem up. So our system here, we have steam, but that's just water. And our device is a throttle. So we're not required for exam 2 or the final to know about throttles. I'm just using this problem as an example for second law. So don't worry about studying for throttle on the final. Water is a phase change substance, and the throttle is an open system device. For the conditions, we have a steady flow process. It says that in the problem statement, but even if it didn't, we could assume for any open system a steady flow process. Also, we need to apply the throttle conditions. So if you look back at your notes, the throttle conditions are: the throttle is adiabatic, there's no work, production, or consumption. We can neglect kinetic and potential energy change as well. For the properties, we have the inlet pressure is 7 megapascal or 7,000 kilopascal, or we can write it as 70 bar. The inlet temperature is 450 degrees Celsius, and exit pressure is 3 megapascal or 3,000 kilopascal or 30 bar. And then we are ready to start solving the problem. So what we're solving for is the entropy generated per unit mass. That's lowercase s gen. Anytime we see that we're looking for entropy generation, or entropy generated per unit mass, or the rate of entropy generation, we're going to be using the second law to solve part of the problem. Alright, so since this is our first problem with the second law, we'll talk about the process of solving for the entropy generation. Usually before we can solve for the entropy generation, we're going to have to go through the process that we learned about in either Chapter 3 for the closed system or Chapter 4 for the open system, just solving the problem in general. So that means we need to apply the mass balance. So we have the mass balance for single stream, one inlet, one exit. We can write constant rate of mass flow through the device. For the energy balance, we can start off with our full energy balance equation, and then we cancel off the negligible terms: potential, kinetic energy, work, and heat transfer. So for the throttle, it's a special device where delta H is 0, or it's also called an isenthalpic device. H1 is equal to H2. So nothing really we can solve yet for the energy balance or the mass balance. Let's keep going and see what we need to do with the second law. So if we look at the second law, again we want to apply the correct version of the second law depending on what type of device we have. So in this case we have an open system and we have a single stream device, so make sure we look at the correct equation. We have S gen, lowercase s gen, is equal to delta S minus sum of Q divided by T sub B. So in this case, we have an adiabatic process. We can cancel off this whole term. There's no heat transfer. So there's no entropy transfer with heat. So in this case, it's really simple to find Sgen. It's just going to be S2 minus S1. So it comes down to just a state analysis where we look up specific entropy at states 1 and states 2, actually the inlet and the exit. So let's look at the inlet. And at the inlet, we have properties pressure and temperature. So we also have a phase change substance. So to get S, we need to look up the phase or determine the phase. Take T1 and compare it to the saturation temperature at P1. So we have steam at 70 bar at the inlet. So go into the property tables. Go down to the table A2, actually it's in A3, where we look up our pressure is 70 bar, so we're going to have to scroll down. Here is 70 bar, and we see the saturation temperature at 70 bar is 285.9. 285.9 degrees Celsius. Our temperature at state 1 is 450, so T1 is greater than saturated temperature, therefore phase 1 is superheated. So we can just go to the superheated table to look up specific entropy at our given P1 and T1. So go down into the superheated tables, A4, and look for the 70 bar subtable. Gotta keep going. Here we see 60 bar and 80 bar. So we're going to have to interpolate between the 60 and 80 bar table. Alright, our temperature is 450. So also unfortunately going to have to interpolate for 450 as well. So here's what we're going to do. We're going to first of all get the specific entropy at 60 bar and 450. So let's do that. Going back over into my notes. I have to do some interpolation before we can do this. First of all, we're going to find S at 60 bar and 450 degrees Celsius. So for that, we're going to need to interpolate. Table values here, we have 440 and 500. So at 440 and 60 bar, we have a specific entropy 6.6853, at 500 6.8803. Alright, so that's going to be S at 60 bar and 450. We'll calculate that number here in a second. We also need to get S at 80 bar and 450 through interpolation. So for that one, we're going to have also 440, 450, 500. So for 80 bar and 440, actually this one we're going to be interpolating at 480, not 500. It's okay, we'll change that. So at 440 and 80 bar, we have 6.5190. Change this to 480. At 480 Celsius and 80 bar, we have 6.6586. Alright, so let's go ahead and calculate those two numbers. Alright, first was S at 60 bar and 450 Celsius. So for that one, we need, I'm going to save this as something, I'm just going to call it SA. So IP 440, R value 450, 500, 6853, and 6.8803. So there's SA. SB, we needed to interpolate between. SA we're going to write down as 6.7178. And then SB, interpolating between 440 and 480 at 6.519 and 6.6586. So that one's 6.5539. Alright, now we can actually interpolate between 60 bar and 80 bar to get our value, which was at 70 bar. So our actual S1, we're interpolating here between 60 bar and 80 bar. At 60 bar, our value of S is 6.7178. And at 80, our value is 6.5539. So S1 ends up being interpolating between 60 and 80, and between SA and SB. Alright, so our value of S1 turns out to be 6.6358. Alright, so we have S1. Now we can go to the exit and try to get S2. So at the exit, we know the pressure only, right? We're only given the pressure is 30 bar at the exit. So how do we get another property at state 2? I'll let you think about it for a second. If we go up and look at what we wrote for the first law, we see something really important here. H1 is equal to H2. So for a throttle, it's an isenthalpic device. This will actually give us a property at state 2, which is H2. And then with H2 and P2, we can define state 2, or the exit state. So our other property is H2, which is equal to H1. So typically you're going to have to use the first law for something in these problems, whether it's a property like in this problem, or maybe it's to solve for the heat transfer or the work transfer. Typically the first law is still going to be a part of these problems. Alright, now let's try to figure out what is H1. So H1 should be H at P1 and T1. We're going to have to go through the same process that we did a second ago to get S at state 1 to get H at state 1. So first we're actually going to have to find H at a value of 60 bar and 450 degrees Celsius. So for that one we were interpolating on 440 at 450 and 500. So our table values at 60 bar, H at 440, 3277.3. H at 500, 3422.2. Alright, that's going to be H there. H at 80 bar and 450. We're interpolating between 440 and 480. At 440 and 80 bar, our value of H 3246.1. And at 480, 3348.4. Alright, so we can get these two values real quick in the calculator. HA is interpolating between 440 and 500. 3277.3 and 3422.2. Alright, so HA 3301.5. HB at 440, 450, 480, 3246.1, 3348.4. So we get 3271.7. Alright, that'll give us our actual H1. Would interpolate between the 60 and 80 bar at our value, which is 70. 3301.5, 3271.7. So our H value is equal to 3286.6. Alright, so now we have H2 value. H2 is equal to H1 is equal to 3286.6. So to find out state 2, we need to determine the phase, compare H value to H sub F and H sub G at P2. So looking up here at P2 is 30 bar. Our value of H sub F, 1008, H sub G, 2804. So we're bigger than H sub G, 2804. Meaning that state 2 is still in the superheated phase. So to find out S2, we need to get S at a value of P2 and H2. So we go to the 30 bar superheated table. Back down into table A4 at 30 bar. This time our subtable is here, 30 bar. And we try to bracket our value of 3286.6 for H. So this number here brackets, these two bracket 3286.6. So we're going to interpolate between these two numbers on the entropy. Alright, so here we're interpolating Our first H value that bracketed was 30 to 30.9. Then our value is 3286.6. The other bracket value, 3321.5. Then for S, we have 6.9212 and 7.052. So S2 is going to end up as, here we have 3230.9. This was H1. 3321.5, 6.9212, and 7.0520. So we get 7.0016. Now we're ready to finish the problem. We found that Sgen was S2 minus S1. So our entropy generated per unit mass is S2 minus S1, 0.366. So that's our value. The interpretation here, does it satisfy the second law? The entropy generated is positive, so it is greater than or equal to 0, then it does satisfy the second law because the entropy generation is positive. This device would be irreversible since entropy generation is greater than 0. And the last thing we want to do is to sketch this problem out on the TS diagram. So here, let's put in our saturation dome here, because we have water. Then we have some constant pressure lines. We had one at 70 bar. We had our other one at 30 bar. And for this problem, state 1 was at 70 bar and superheated. And S2 is bigger than S1 because we got S2 minus S1 is a positive number. So here S2 should be to the right of S1 and it should be superheated. So there's a good spot for state 2. Just connect the dots with a dotted line because we don't know the exact process path. Alright, and that wraps up this problem and the sketch. So key thing for this problem was we were applying the second law to an open system. We found that application of the second law also typically involves application of the first law as well. So we're basically solving the first and second law for an open system process, and we determined the entropy generated per unit mass.